Okay. All right, so the definition of a half-life is the rate at which a nuclei decays or the time that it takes for it to happen. Okay, so once again, if I have my radioactive atom here, okay, the half-life is how long does it take for the alpha particle to come flying off. Okay, now it's interesting because it's really unique for each individual sample. Some things have a crazy long half-life. Like today, we'll do a little simulation lab of carbon-14. Carbon-14 has a half-life of 5,730 years. Very, very long time. Other samples, like some of these brand new elements that are very, very radioactive, have half-lives of like less than a second. Okay? What this means by the idea of half-life is that if I have a 10-gram sample of carbon-14, okay, every 5,730 years, half of that sample will decay. Okay, so now I'm down to 5 grams. Then in another 5,730 years, another half of that sample will decay. So then we have like 2.5 grams. And it keeps cutting in half, cutting in half, cutting in half. In math, we call this an exponential decay. Because if you know, like labeling graphs, it's exponential, meaning it's just getting lower and lower, closer and closer to 0 as you can. Now, mathematically, does an exponential graph ever hit 0? No, right? You just keep cutting in half, cutting in half, cutting in half. Well, now that we're talking about actual things and not just numbers, technically a half-life graph can eventually go to 0, but you got to get all the way down to 1 atom left before that would happen. Which, if you think of how many atoms are even in just, a handful, could take a really long time, depending on what the sample is. Okay? So one of the cool things about this, particularly with carbon, is they use it for this thing known as carbon dating, where that's how they can tell or estimate how old something is. Because everything that lives or was once living has carbon-14 inside of them. Okay, just a reminder that if you're on your phone during the lesson, you lose the right of being able to take the test again. Okay, and when I'm standing and you're sitting, I can see you on your phone very easily. Okay, thank you. Okay, so everything has carbon-14. We have carbon-14, animals have it, planets have it, anything living has it. Once we die, okay, we don't generate new carbon-14. And so when they find something that is dead or lived a long time ago, they can measure how much carbon-14 is inside of it to estimate how old it is. Yeah?
How would they know how much it started with?
So it's like a percentage thing, right? Because they can say, okay, we know that percentage-wise it would have started with this much, and so now it's down to 50% of the original. Does that make sense?
Yeah.
Which means for carbon, it's been about 5,730 years. So, great question. Yeah, McKay.
So when you say it has half its original amount, would it be like carbon-14 becomes carbon-7, or just say carbon-14?
So in this case, it's doing a beta decay, right? So what does carbon-14 turn into if it does a beta decay? Whoa, that was a weird number. Oh, wait. So in a sense, it's not carbon anymore. You are right now that it is 7, but it turns into nitrogen. So the carbon-14 inside of us that decays actually turns into a new element of nitrogen. Is that what you were asking? Kind of what it turns into? Great question. They actually, though, there is some flaws with this system of dating. Obviously, if something is not very old, like if it's less than 5,000 years old, this isn't a very accurate way of measuring. Or if it's really, really, really old, like the dinosaurs, this doesn't work because the amount of carbon-14 inside of them you almost can't even measure. So for the dinosaurs, they use a different element of uranium because it has an even longer half-life. I think it's over 10,000 years. Don't quote me on that. I'll double check. But kind of interesting. Okay. So once again, this right here is our idea of an exponential decay. Okay, where I start with a whole. After one half-life, oh wait. This is uranium. I was way off. uranium has a half-life of 1.3 billion years. So that's why it works for like the dinosaurs. Okay, but you notice that every half-life cuts in half, cuts in half, cuts in half. On your paper, you should have a little number line. They didn't leave me very much space, but I want you to draw a picture on that little number line with me. I'll draw mine right here. Just to have another visual of what's happening, okay? Sorry, you're gonna have to kind of squish or maybe draw on top of some things, okay? So let's say, for example, today, we were walking around outside and we found a rock of uranium. It's not weird, right? Okay, let's say my rock of uranium has that much mass. So draw a little bar graph here on that first dash.
A bar graph? Can we just draw the I can't think what it's called. That graph right there.
Well, you already have that graph on your paper,
Oh, okay.
right? I just want you to look at it in a different way than how that graph is shown. It's showing the same information, okay? So this would be like at day 0. Okay? At 1 half-life, how much of my sample am I going to have left? Half. So take your bar and cut it in half. At 2 half-lives, how much will I have left? A half of that, meaning how much from the whole? I'd have a quarter left, right? So on and so forth. But what I want to make sure we understand, and it kind of goes very well with McKay's question, okay, is where did the other half go here? What happens to it? Good, so it's turning into something new. In this case, it's turning into thorium. So either get a different color, pencil or pen, or like label it differently. But I want you to recognize that there still is this other half, right? Matter cannot be created or destroyed. The rock doesn't disappear, but it changes into something different. It changes into this case because it's alpha decay, I think, right? So it's changing into thorium and alpha particles. So just draw the other half of the bar, a different color or label it differently, to show, hey, these things aren't actually going away, but chemistry is all about change. Now, kind of another cool connection here. Has anyone in here ever had a bone scan before? Any people? So with a bone scan, they use this in a variety of things. The first thing they do is they actually inject you with a radioactive sample. I don't know if you know if this was happening to you when you had it. Hopefully they told you. But they inject you with radioactive iodine, I believe is what it is. Okay? What happens is that chemical latches to the calcium in the bones, and then the scanner can detect it and it lights up the bones. It's a way to kind of detect things in the bones that an x-ray doesn't show. Like I had one when an x-ray didn't show a fracture all the way. They did a bone scan so they could see it. But this sample that they put inside of you has a half-life. So it's not like you're still radioactive today, because after so many days, that radioactive sample is gone. They also use them for a variety, sometimes for cancer treatments, they'll use radioactive samples. But same thing, it's not like it's just staying inside of you and you're glowing, right, radioactivity, because of its half-life.
That'd be cool.
Yeah.
Before they injected me with the iodine, they like explained to me like three times like what's it's gonna feel like when they inject it. Like it's gonna be a cold rush, then you're gonna get a fever. And they explained this like 3 times over.
Yeah, Jim.
Wait, so like, since uranium, like the half-life, because of that, half of it turns into thorium or whatever. Would then thorium have a half-life and then half of the uranium turn into everything?
Yes, sometimes. So we'll learn next time how there often are these things known as decay series, where something decays into something that's actually still radioactive. And it will continue to decay until it becomes not radioactive. So next time we'll talk about what stops the process. And yeah, some of them will go through, especially uranium, goes through almost a 10-step decay process before it actually is stable. So yeah, great question. Another kind of fun one that's not in a sense radioactive, but it does have a half-life, is caffeine. Caffeine has a half-life inside of your body of about 5 hours, which one of the teachers kind of brought up. I wonder if that's why they call it 5-hour energy. I don't know if that's where they got its name from or they just happen to call it that. But caffeine has a half-life where it takes so long for it to actually go away, which means if you're constantly drinking caffeine, it's never actually fully out of your system, which I don't know if is a good thing or not, but you can decide, I guess, for your own health. But it's kind of interesting to see. So, any questions on what half-life is?
Imagine going to like a glow in the dark party and then you just like light up.
Because you're radioactive.
Yeah, that'd be so cool.
Any other questions for now? Okay, take a look at that pink packet that says Penny Half-Life Lab. You're welcome to put your notes away.
Are we supposed to solve a penny?
Are we dissolving a penny?
Yeah.
Not today.
Not today.